Okay, so thank you, Eduard, for the introduction, and welcome to this year's first SIRIUS lunch. And these are always short introduction to something that is happening within SIRIUS, some result that is of general interest, or some technique that we are using, developing, or are interested in. And today I want to talk a bit about ABS. This is a reprise from a talk that was given almost 2 years ago. But since there are a lot of new people now joining, it's nice to go through the basics once again. So the outline is basically what even is that? And also a bit generally about modeling, what is that and what do we try to achieve? And then what kind of models is ABS good at, and then a bit about using it. And there will be lots of examples, no detailed code walkthroughs, but just to get a feeling of what we can do with that small language. Okay, so ABS is a modeling language that has been developed in the ex-PMA group. And there are some people who are still here in the floor who are very instrumental, Olaf Uwe, Einar, Martin Steffen, me, and others. And it's been carried through 3 European Union projects. So there has been a lot of funding over the years to work out, okay, what can actually work in modeling, what can we do, how can we experiment with actor-based semantics and asynchronous communication, and then also implementing things and making case studies to check if things actually work. And then it worked reasonably well, so it's been used as a modeling tool and also as a research and teaching language by various groups from Germany and Darmstadt. So there's always some new crazy stuff that's coming from Eduard's direction in type systems, etc. And kind of the main branch of the language is currently maintained by me. So I'm integrating things, bug fixing, etc. So modeling can mean many different things, and models can be many different things. So there's entity relationship models, there should be an H here, which just model what are the entities that are in the real world and how can we store them in a database and query them again. Ontologies are similar, except more powerful and cooler. On the other hand, process calculi are usually saying, okay, this thing exists and talks with this other thing, and then they change the state in some way. But those then are good for systems that change, like, a database or an ontology talks about the world as it is and how it is structured. The process calculi says, okay, here's a thing, and now it, in response to stimulus, it becomes something else. And then, of course, there's differential equations that have been used very successfully for many decades or hundreds of years to model physical systems. Like, why did this bridge collapse? Okay, it responds to a periodic impulse in a certain way, and then there's resonance, and then it collapses, and so on. So, and the message there is that depending on what you want to model, you choose a formalism. So, what kind of models do we want to write with ABS, and what kind of insights do we want to gain? And modeling with ABS is a way to gain insight into complex systems. So in ABS, we describe the behavior of actors in the computer science sense and their interplay, how they talk with each other. And we mostly do simulations to discover complex, emergent, surprising behavior, right? So even if every actor, you look at the code of it, you can understand it, but then you let it run, and then this is surprising what comes out of that. So my favorite example of that is the Monty Hall problem. Basically, if you're on a game show, it's a well-known problem that is easy to describe, but has a counterintuitive behavior. Right, you're in a game show and there's 3 doors and you're asked which door do you want to open. Behind one of the doors, there's a car and you say, I want to open the door number 1. And then the host opens door number 2 and shows you, there's no car between door number 2. Do you want to change your guess? Do you want to stay with door 1 or do you go switch to open door number 3? And the question is, what should you do? Is it better to switch, or is it better to stay with your choice, right? So, and there is, of course, analysis for it's called Wahrscheinlichkeitsrechnung, probability calculations that tell you what is the better strategy. But we can also just write down everything. So we have a host interface that has two methods that are called by the participant. One is called guess, and they say I want to open door number 1. And what this method does is returns a door that is the wrong one, that is not the right guess. And then there's a method open, and again we say which door the participant wants to open, and that one returns either a goat or the car, where the car is the good outcome and goat is not. So the contestant then, they get handed a host to play with, and afterwards we can print a summary of how much they won. And then we have two subclasses, one switching contestant and one non-switching contestant. And these two implement two strategies, right? So the switching one guesses an X. The host tells him, no, it was not the Y. And then he picks the Z, which is not the guess. And then he gets either back a goat or a car. Whereas the constant guy, the non-switcher, he guesses an A. The host says, no, it's not B. He picks the A that he guessed, and he gets back a goat or a car. And there is, if you want to look at the whole thing, here is a tiny little website that is in the ABS homepage, where there's the whole code. So here's the host. I don't go through it. So if you're interested, you go to the website, you see the whole thing. And then it's the surprising or non-surprising outcome. Is that if you run the model, the switcher roughly wins 2/3 of his guesses, and the non-switcher, the constant one, wins only 1/3, which is what, and the concrete numbers will change a little bit, but you can see what's happening, right? So this is an example of easy to understand actors interacting in easy to understand ways with a non-intuitive outcome. And this is something that that is very nice to model in ABS. Right. So there are some strengths that we have kind of been designing towards. This one is that you have seen a little bit of the syntax. It's very Java-like, so it's easy to pick up. Then there's a pure functional layer where you model your data structures. So you don't need to use classes if you just want to model some person or message request thing. That one has no side effects and can also be used as a specification language. So if you want to write down some pre or post conditions, you can use the same expressions that you use inside the program. And that's also good for formal analysis of that language, which is also something that has been done, for example, by Eduard and the students. Right. And then it has a natural and safe concurrency model, similar to a language called Erlang, which also has this claim to fame that we just send messages to each other and nobody can overwrite things. So there's no spooky action at a distance, where in Java, you have to always lock things. Otherwise, some other thread might overwrite your state or whatever. The language makes it so that you cannot even write that thing that would lead to a race condition, right? And then we have a declarative time, and this should be a resource model, resoruce, which is an Italian word for resource. It's not, it's just a typo. And that is, for example, used now by Gianluca to model deployments on a Kubernetes cluster. So he models Kubernetes and the application that he runs on it, and he simulates it in ABS, and he gets back how much is the load of each container, and how long would it take. And it's very exciting for me because it's a very nice and large-scale case study that I can't wait to see what he comes up with in the end. But it's very encouraging. So it seems to work. It's really exciting. So I want to talk a bit about some more models. Also about how to visualize things, because just printing things on the terminal is not very exciting. So we have a model, ways of getting data out of a running model by HTTP requests that give you back some JSON that you say in the application what you want in the model. And very early, it's recently been merged into master, is getting data in from an SQLite database. So as I said, we have a dense time model with a logical clock. What does that mean? You just say, okay, the next step here takes 10 time units. Okay. And then if you have two actors running in parallel, one says, okay, the next thing I'll do is in 10 time units, and the other one says it's in 5 time units, then things will happen as you expect, first in 5 and in 10. And these things compose again. So you can throw together actors as you want, and there is no way that they don't have to care or know about each other what they need from the clock. So it all just works together. And what I want to show you briefly is a water tank. So we have a small physical simulation, which is just basically a tank and its controller. So there's always water running out. And if the water is too low level, then I turn on the valve and then it gets filled again. And then when it's too high, the level in the water tank, it gets shut off and then the water sinks again. So how does that look? I will briefly switch to my editor. And here, I'll just quickly start the thing. And what we see here, we compile it. And then we run it. And here we see that the model is now listening at this URL, localhost 8080. And when I switch to the browser again, and we see the behavior over time. So here we have the water level. And here we have the status of the valve, right? So the valve is closed, water rises, then it's, it switches, water level falls, and then rises again, falls. So that's just a discrete time event simulation. And actually, again, Eduard has managed to integrate also a continuous time simulation. What was it? I think it was Modelica, right, that you integrated. So that one's not in the main.
Yes.
Yeah, thanks. So that's not in the main line yet, but you can express also differential equations and then say, okay, please wake me up if there's this or that condition in my continuous time domain. And then you can also do the same thing here so that the continuous water level falls, and once it falls below a threshold, then the controller is woken up again and gets to interfere. Okay, so that's a way of visualizing things. So I said that what we do is we have HTTP requests, and I want to show that very briefly. So what we see here is that's the model running in ABS and listening to whatever comes. And what we see here is just the HTML that is in the browser. But what we can do then is we can ask, okay, what objects are in the model that we can interfere with? And it gives me back a list that has a single object called water tank. And okay, hey, water tank object, what methods do you expose? It says, okay, I have one method is called get valve level and history. It doesn't take any parameters, and it returns a list of pairs of integers and floating point numbers. And that's the output of the result of that. So it's just a large JSON list. And here we just see how this one looks inside the model. So I create a water tank object, and I just say, okay, this one should have an HTTP name with water tank, which was what you saw before. And here again, in the interface of the water tank, I'd say, okay, this method get valve and level history should be callable via HTTP. And that's all there is to it. So again, the model is unchanged, but just by having some annotations here, I can say, okay, this thing should be peekable from the outside. Right. Okay, so we already saw this slide. So visualization of a model, if it's not in ST text, typically it's in the browser. And these JSON data that we saw already in the model, that's automatically converted from ABS, so you don't have to do any interfacing. Yeah, and there's a lot of things you can do, because also there's arbitrary JavaScript that you can have there. So for example, what it could do is if you have something that you want to visualize and it's geodata, this is a very, very simple, this is just here, this is just, okay, what are the coordinates, and give me all the map objects that I want to see, and I just say, okay, there's two things. One is the city hall and the opera house in Oslo. So we can throw those on a map. Okay, reload, and we have this. So if you have any geometric data or mapping data in a model, we can visualize that as well. So here's the city hall, and here's the opera house, which is just what the two data points I returned from my model. Yeah. So this one was just a proof of concept, where I was curious, okay, can I actually do this? And yep, I can. Yeah, and I think I will skip the calendar, time and dates, which is just the same thing if you don't have geodata, but if you have real dates, not like the logical clock off that goes from 0 to whatever. We also figured out a way to connect the logical clock of ABS to quote unquote real real data. So, but that's not very exciting. It's just a way of saying, okay, the clock number 5 in my model should correspond to 12 p.m. on the 2nd of February, something like that. Okay, and finally, the last point I wanted to mention is that a lot of times in the models that have been written in the various projects and in the case studies, there was some kind of very large input data that was just some, for example, sensor readings in the real world, or genomic data, or logistics data, you know, on the so-and-so of December, the container number named so-and-so was transported to this point in time, and so on. And this was always awkward to encode in ABS. So what I did was then also to make it easier to import that kind of data. Because one thing about models is that they're not usually interactive. So if you read the ABS documentation, you will not see any file IO or, you know, user input, etc. Simply because it was much more planned as something like a model checker, where you set up your scenario, check, okay, this all is very meaningful, this is what I want to know, and then you run the simulation and see what comes out. But you don't want usually to have it interactive, because then you can't reproduce what is there, and the next time you run it, something else comes out. So this is very not something you want, except when you do. But you do want to have large amounts of data to specify what should happen inside the model from one point in time to the next. And the way to do that is to prepare the data in advance and store it currently in an SQLite database. And then when you start the model, again, you can translate what is in the database automatically into an ABS data structure, right? So for example, I have here a way to define a person inside ABS, and the person has a name and an age. And then also, so this should read the list person. And then I just say, okay, from this database that is next to my model, I can run this query here, select name age from person, the age is 23. And since that thing here returns a name string and an age integer, which is the same as the string and the integer here, I get back a list of persons. Okay, and that approach works in theory and soon, hopefully, also in practice with any data source that provides this kind of uniform rows of structured data, CSV files, Sparkle queries, and also newer data files like Parquet, which is a very nice data format for this kind of data from the Python world. Yeah, and so I'm excited about the next round of case studies because finally we'll have a way of just preparing the data, hopefully by the domain expert or as a data dump from somebody else. Usually you get the data via Excel files. So we just throw them into ABS and run our models and say, okay, with this data, this thing should happen. So this will be very nice. Right. And so in case you got very curious now, you should check the homepage, absmodels.org. And one of my proudest achievements is that it's actually documented. So Crystal Dean, who you know, who is now in Bergen, and me had this pact. We meet each morning at 9 a.m. and spend 1 hour writing a manual. And after 8 or 9 months, actually, we finished. And it's now kept up to date. So every new feature that goes into the language is also documented and tested. So this is a source of very great pleasure for me. Yeah, and of course, it's open source and can be checked out here.